Okay, the next speaker is Shivani Tiwary. She received her bachelor degrees in bioinformatics from Dr. D.Y. Patil University in India. Afterwards, she moved to Germany and pursued her master degree in BIT Bonn. And then she moved to Munich for her PhD in Cox groups at Max Planck Institute, sorry. And then she working on the implementations of machine learning and deep learning for analyzing biological sequence and mass spectrometry data. So today she will talk about the MaxQuant output tables.
So welcome to the lecture. In this session, we will talk about MaxQuant output tables, and we'll try to get familiar with the tables generated by MaxQuant after the MaxQuant run is done. And feel free to raise hands to ask questions in between. So where you can find the output tables when your MaxQuant run is done, then go to your project folder, and there you find a combine folder, and in that you find a text folder, and there you see all the MaxQuant outputs. And this you can open in any text files, Excel, or whichever is your favorite editor, or in Perseus for further visualization and analysis of your data. Also, another way is to go to MaxQuant, and you note a visualization tab there, and you see your table navigation, and then you have your table view. So here you can get the first impression of your output tables, and it's very convenient to just look what information is there and how was your experiment. And yep, so I would like you to note this last entry in this folder, which is tables.btf, where it has all the description for your column entries. So there is a short summary, and you have column names and their short description. So whenever you get lost in between the tables and you don't know what does it mean and what does it say, so you go here, and then you can read the description and get the idea about it. So it's very useful, and always go there. So now we should start how our proteomics workflow is. So LCA proteomics starts with the, liquid chromatography, and then you have full MS, and from there you choose your precursor, and then you do your MSMS. And then MaxQuant and Andromeda interpret those MSMS and get the peptide identification. And from that, you get your protein groups. So this gives you identification level of your experiment. And this comes from the features, which are the 3D object described by Jürgen earlier. And this, you get the information from scans. So, and above all of these information is the metadata information, is your all parameters which you use for your experiment. So this is reflected into MaxQuant output tables, and you can see that these tabs are there in visualization tab. So scans, identification, features, and metadata. And these tabs have their sublevels, which are corresponding to your output table. So for scans, you have MS scans, MSMS scans, and MS3 scans. And then go to identification scans. Here, this is the most useful level and tab for us who wants to do data analysis and or get to know about your proteins. So here you can get to know about your protein groups, PTM sites, your modification-specific peptides, and evidence and MSMS. Next is the feature level. Here you have tables for all the features, which are the 3D objects. And you have matched features if you do match between runs. And up next is metadata, which have all the parameter information. So you get a summary table and a table for your parameters, which you use for your MaxQuant analysis. So next we will spend some time on the identification tab, as this is the most useful level for most of us who are interested in just knowing what are the proteins they got from their experiment, its identification and quantification. So here, what information you get is all identified protein groups from your all experiment and throughout all the runs. So you get the information about protein properties, such as physicochemical property of protein, such as molecular weight. Then you get all the peptide counts, which were used to identify the proteins. Then how they were identified by MSMS or by match between runs. What is the sequence coverage? So how many peptides were included to identify protein. Then peptide counts. So how many peptides were there across the experiment and fractions, and its Andromeda Q value and score. Also, you get quantification information, such as intensity. And if you do label-free quantification, then you get label-free intensities. And for isobaric, you get your normalized ratio, as for example, for TMT. So here you can see that for label-free, there are new columns generated, and these are the intensities corresponding to label-free experiments. And then for isotope level, such as for SILAC, you get ratios from heavy to light, or heavy to medium, if you choose that. And then you can also get the variability information. Then you get the count, so the peptides which were involved in that ratio, and then you get the isocon. And for TMT, there are more columns here, and these are corresponding to the reporters for TMT channel. And here you can zoom into a protein table, and you can see that it is identified by MSMS or by matching, or it's not identified if it's blank. And here you can see the intensities. And up next is the PTM sites text. This is similar to protein group text. And here you have information about modified protein sites. So you get the localization probability and number of site modifications. You also get your intensities and site occupancy. And this will be discussed in detail in PTM session, and so you will get more information about this later. And so conclusion from this tab would be that you can use these tables and put it into Perseus and get your visualization done, and data analysis, downstream bioinformatics data analysis can be done. And you can use this information for classifying it and for Go enrichment, etc. So this will also be discussed because we will be using this table and using it in Perseus session. So this is a good point, so that we just at the same page. So protein groups comes from the identified peptides. So each group has many identified peptides. And these identified peptides have many evidences. And these evidences have information from MSMS scans. So this is a cascade level, and this information is shown reflected into MaxQuant output tables. So each table is also linked to each other, and you have information about each level in the MaxQuant output tables. So up next is peptide table, where you get the information about the identified peptide sequence throughout the experiments. So you also get the information about modified sequence, its core, and then properties like mass, length, amino acid counts, and then first and last amino acids, its cleavage window and number of miscleavage cleavages so that you know how your protease is working. And then, because their output tables are linked to each other, you can also get the protein-centric information. So in peptide tables, you have information from protein tables. So you get your protein identification, and also you know the start and end position of peptide within the protein. So you can map your protein peptide information to protein identifications. So also you can get the peptide quantification, so you can get the intensities and ratios if it's applicable. Here you can see a use case for peptide table that you can plot this distribution of amino acid length, and you see that most of the amino acids are of 10 to 15th, which is true for trypsin digestion. So you can say your protease is working fine. Another use case would be to know the miscleavage rate. So here you can see you have 0 miscleavages rates. That means your miscleavage is not, your protein is cleaved well. And you can also get the cleavage window so that you just know that which protease is this and it's working fine or not. So here we see it's trypsic. And so another use case would be if you have peptide table, you see start and end position, and you can plot this to know the full length, the protein is identified by full length or not. So here we see it is full length, but there are a few gaps, but we almost identify each peptide sequence. And also, if you plot the start position with the intensity, you can get to know the abundance of the peptide. And you see that here in C-terminus, they are more abundant than in the N-terminus. So also, another use case can be to see your fractionation efficiency. So if you did protein fractionation, so you want to know this peptide belongs to which fraction, so you can just plot a heat map, and you can plot unique peptides in each fraction, and you see that each peptide sequence belongs to either 1 or 2 fraction, and these red ones are the abundant peptides, and green ones are not non-abundant ones. So this fraction is sharp enough, and it's not identified throughout the fraction, so this is good to know. And then let's zoom into this peptide table. And here we see that for each one peptide sequence, you have many numbers from different experiments. And these numbers says how many evidences do you have for each experiment. So as I already said, that for each peptide sequence, there can be many evidences. So next, we go to evidence table. So as we already discussed, we have protein identification, which comes from many peptide identification. And these evidences are information coming from either the sequence was identified by MSMS or by matching, or does it have different charge state, +2, +3, or is it from modification or not? And for each evidence, we get meta-information, which is EMS-centric, so such as the mass error, the score, retention time, and other parameters. So let's zoom in again into the evidence text, and here we can see that for the same peptide sequence, we get the information either it's from modification or for unmodified. Is it identified by what type, multi-MS, MS, or MSMS? And which charge state, so 2 or 3, and what retention time. So another use case would be to find the effect of temperature on retention time. So you can plot the retention time against the uncalibrated mass error, and you see the plot, the density plot, and these are centered. So there is not much fluctuation in the temperature, in the retention time. So this is good, but if your plot looks something like this, then there is something wrong, and then you should check where was the temperature varied or not, and what should you repeat your experiment or not. So this is a very good thing to check. So you just have to load your evidence table into Perseus, and just by a few clicks you get this plot and you understand the experiment performance. So next use case would be to find the retention time reproducibility. So if you have 2 runs and you want to see if the retention time were same or not, and here in this case you see they all are in the same line, so it's not varying much, so this one is good. You can also find, so if you are using different columns, so this working nicely or not, and you can plot the histogram again and see the peak, and here it's broader, so it's clear that column 2 and column 3 were not working nicely. Also, evidence text, you can use it to find the resequencing rate, so how many MSMS counts were there. So you can find if the resequencing rate was better, or I mean, it's good or not, if your dynamic exclusion is working or not. So dynamic exclusion is what you take one MSMS and you make a list and you try to not sequence it again. So here we see that most of the MSMS were sequenced only once, and 2 were few times but never 3. But there is 0 MSMS, which means that it was found by MS match between runs. Yep. So up next is the scan tables. And here we get information about the MSMS scans and MS3 scans and MS scans. So these all names are same, don't get confused. The MSMS text in identification table tab is all the MSMS identified, whereas MSMS scans.txt is all the MS, irrespective of it was identified or not identified. So in the identified MSMS text, you get the fragmentation type, your CID, HCD, ETD method, which method was used, then the filtered peaks, which we will talk later, and match fragment ions, and the annotated peak and intensity fractions, and the mass deviation. In all MSMS events where it was identified or not, but you still have all the information, which is MSMS scans table. So here you find ion injection time and AGC fill parameter. So ion injection time is the time required when you injected your ion, and AGC fill is the parameter where you waited in C-trap, and how was it equal to your target or not. Then these are the parameters we will discuss in detail: precursor apex fraction, precursor ion fraction, and precursor intensity fraction. And if you will open your MSMS scans table, maybe you see them as 0, these columns. So maybe you have to check the calculate peak properties. So coming to precursor apex fraction, this gives you an idea of how far your MSMS event was from the apex. So if it is 1, it means that your MSMS event occurred at apex. If it is 0.8, it means that it was not at the apex, but still close. But if it was 0.1, that means it was too far from the apex, and you should wait for some more time for your next MSMS event. Then base peak fraction is another column which is similar to that. But here, this gives you an idea about the dynamic range. And so base peak is the most abundant peak in your survey spectra. and you want to find the relative between the intensity, which is going to be fragmented, a peak which is going to be fragmented, relative to your base peak. So if your base peak fraction is 1, that means you are fragmenting your abundant peak, which is 652. But if it's 0.5, and you are fragmenting this one, which is like 50% of the most abundant peak. And then if you find it 0.06, that means it was very low abundant in this survey spectra. So you might not use this one. So yeah, this just indicates the range of your precursor selection. And next is precursor ion fraction. It gives you the ratio of your total target ion in the isolation window. And so here in isolation window, it's not true that you will always have the target ions which you want, but there will be also some contaminant or some other peak which came within this window. So this information is useful for TMT labeling because there is the problem of ratio compression. So you would like to know your PIF, which means how the ratio of your target ions with the total ions. So you can make a distribution of your PIF and then decide for your next run that what value you want to keep it. So you can give your PIF information here. And next is you can use spectral MSMS scan to check spectral quality. So filter peaks are the top n peaks per 100 Dalton. And these are the peaks which we selected for database search. So the filter peaks are abundant in identified, and these are less in unidentified spectra. And the mass by charge ratio distribution is broader in your filtered, in your identified spectra. Yeah. Also, MSMS scans will help you to find the spectral quality by knowing the intensity ratios. So we know that the precursor should fragment, and the fragmented intensity should be the sum of the precursor intensity. So it will help you to know how is the transmission efficiency. So ratio should be always 1 of your precursor to your sum of the fragmented intensity. So if you see this cloud going down, that means your machine is not fragmenting properly, so you might need to change or clean it. And not transmitting your precursor to your MSMS fragments. And you can also plot against the base peak intensity, which means that how against the abundant peak. And yeah. So next would be MS scans, where you get information about the scan number, your retention time, and ion injection time, and you can get the acquisition cycle, where cycle time is the time between 2 spectral survey, and you can also get your MS count. So you can plot both of them to get the idea how it goes across the gradient. So how the MS counts gradient is, and how the cycle time is. So when the cycle time is 0.1, you don't identify so many MSMS, but as you go on, you see that you identified all the you took all the top n peaks here. So up next is feature tab. And here you get information about all the 3D objects, all the features, and also information about the matched features, which are identified by match between runs. So they are the features which are present there at the same retention time. So the table name is allpeptide.txt, and it has all the detected LCMS features. So for example, mass by charge, charge intensity, retention time, and your LC peak length and shape. And here you can plot the intensity distribution. I think this was shown like so many times until now. So you know that the gray one is all the LCMS features, and you can then color code your targeted for MSMS fragment, and then this is green one is your identified one. So if the gray one is more, I mean, you have to play around with your parameters and your instrument, and you should try to get more less gray area. So up next would be the highest is the metadata, where you have all the summary and all the parameters for this experiment. So summary text includes the number of identified peptides, the number of detected isotope patterns, and your identification rate for your MSMS, and the resequencing rate. And here in summary text, you can see all the MSMS information, which are the MSMS submitted. So do you know why MSMS submitted is more than MSMS? It's mostly because when you submit for your MSMS identification, when you don't know the charge information, you give your additional charge, so all the combination of MS with +2 or +3 charge. And then you can use the summary text to know your instrument performance. So here you can see isotope patterns and absolute mass error deviation. And if it's deviating a lot, then this means you should clean your instrument. So if you think there are too many tables, you can check this out, and these tables will not be written after the MaxQuant run. And so this is the summary. So you have your 4 levels, and you have different tables. And then so we have to know that each table is also linked to each other. So you can find the identifier for each table, and then you can go to this identifier into another table and then match them in Perseus and use the information from each other table. So for example, if you have protein groups table, there will be ID column where you get the ID for protein groups. And then you can go to peptides peptides table. You will have peptides ID, and then you can match and use them together. And this you can do easily in Perseus. I think it will be explained in Perseus session, so I'll not do that. And thank you so much.
Are there any questions?
Yeah, so I talked to Professor Cox about this before, but yeah, there are many output tables. And I wonder, since there are so many already, couldn't you include some information about the non-normalized LFQ intensities? The reason why I'm asking for it is because I'm always normalizing, but I've done a multi-dimensional scaling plot after normalizing, and I can still see some batch effects among my samples, which ideally should be normalized away when I apply it. So I'd like to look at the non-normalized LFQ intensities, and maybe I want to try another normalization method, or maybe even see if I should exclude some sample that shouldn't even be in the normalization. Would it be possible?
I think you can.
I just repeat the answer from yesterday. So in principle, it's of course possible, but the problem with this is that we don't want to inflate the tables too much, right? So that's the only reason why we don't have all possible information in tables, because at some point they are not really handleable anymore. And then on the other side, for people who are specifically interested in this kind of information, there's actually a way to generate it, right? You just would have to rerun MaxQuant, basically. And since probably not everybody of the 217 participants want to see this, what you want to see, I would assume you're probably a minority. I would say it's probably a good enough solution that you have to take the burden now of running it twice, but it's for the benefit of the others who still have small tables and handleable tables. We always have to find a compromise in these situations, basically.
Yeah, I understand. It's just that, yeah, there are many tables, and I think most of people are just using the protein groups table, right? And they don't go into the other tables too. So
exactly. And this would actually would add to the protein groups table and would make this bigger, right? So that's why we're a bit hesitant to.
Yeah, because I thought it would be nice just to have an extra file saying the non-normalized .txt.
Okay, but then everybody comes with his extra file that he wants, and then we have 100 extra files, and nobody knows anymore what is in these extra files.
Yeah. Okay, I will rerun.
Sorry about that. Sorry.
1 week only, so it's okay.
Okay, if there's no more questions, next thing's Shivani.